Let's do part A. Here we write the population function n of t, which represents the number of bacteria after t hours. So we use this basic population model, that is n of t equals n of 0 e raised to the power of rt. And n of t represents the population after t hours. This is population after t hours. And n naught represents the initial population. R represents the growth rate, and T represents the time in units of time. It is hours for this question. So let's plug in the values that is given in this question to write down this population function. We are given that initial count is 8,700. So this basically represents n naught. And then we are also given that after 1 hour, that is when t equals 1, the population is 10,000. That is n of t equals 10,000. So using these two information, we have to find the population function. Otherwise, we will also have to find the growth rate first, and then we can write the population function. So let's do that. So I first write n of t, and this equals, I plug in n naught, which is 8,700 e raised to the power of rt. Now I plug in this information, that is when t equal to 1, n of t equals 10,000. So therefore I put 10,000 for n of t, or otherwise this is n of 1, because when you plug in t equal to 1, this basically becomes n of 1 equals 10,000. So on the left side I put 10,000, and this equals 8,700 e raised to the power of r times of t is 1. So let's evaluate r from this expression. We have 10,000 equals 8,700 e raised to the power of r. I divide both sides by 8,700. I divide by this quantity, and so on the right side these two will get cancelled. On the left side I can just cancel the extreme zeros, the two zeros, and so this can be written as 100 over 87, and this equals e raised to the power of r times 1 is r. Now to determine the value of r, we have to apply natural logarithm to both sides, that is a natural logarithm of 100 over 87, and this equals natural logarithm e raised to the power of r. Now using the power rule of logarithms, we can put this r in front, that is this will come multiplied with in front, and so therefore in the next step I can write this as natural logarithm of 100 over 87, and this equals r times of natural logarithm of e. Remember that the natural logarithm of e equals 1, so that means we can replace this quantity by 1. So r times of 1 is going to be just r. So you can just ignore this. Just remove this and just put r over here. So basically we got this expression for r, that is a natural logarithm of 100 over 87. So we can plug this into the calculator and get the value of r, and when rounded to the three decimal places we get r approximately 0.139. So this is the growth rate, 0.139. And so therefore we can write down the population function, that is n of t, and this equals n naught, which is 8,700 e raised to the power of rt. So now plug in the value of r. So therefore it becomes 0.139 times t, it is 0.139 t. And let me just write this a little bit clearly. This is basically n of t. This is the function which represents the number of bacteria after t hours. And this answers the part A question. In part B, we should find the number of bacteria after 2 hours. That is when t equal to 2, what is n of t? And this gives the number of bacteria after 2 hours. So let's plug in t equal to 2 into the population function. So therefore we get n of 2, and this equals 8700 e raised to the power of 0.139 multiplied by 2. And so this becomes 8700 e raised to the power of 0.139 times 2 is 0.278. This is 0.278. So we put this expression into the calculator and find its value. And when we do that, we approximately get 11,500. And this value is rounded to nearest 100. This is rounded to nearest 100. So we see that after 2 hours, there are about 11,500 bacteria. And this answers part B question. Let's answer part C. Here we have to determine after how many hours the number of bacteria will double. So it's basically asking the question, we have to determine the value of t such that n of t equals twice the initial amount. The initial amount is 8700, and so this equals 8700 times 2 equals 17,400. So this is the double of the initial amount. So let's plug in n of t equal to 17,400 into this function and determine the corresponding t. So therefore this becomes 17,400, and this equals 8,700 e raised to the power of 0.139 t. And we know that the 17,400 is twice the 8,700. So when we divide by 8,700, we get 2 over here, and this will get divided by 8,700. So it becomes 1. So we have the equation 2 equals e raised to the power of 0.139 t. And once again, we have to apply natural logarithm to determine the value of t. So when we do that, we get natural logarithm of 2, and this equals natural logarithm of e raised to the power of 0.139 t. And so this gives natural logarithm of 2, and this equals, we can apply the power rule. So therefore, this expression comes in front. So it becomes 0.139 t times of natural logarithm of e. We know that natural logarithm of e is 1. So I can just remove this from the expression. And now to determine the value of t, we divide both sides by this quantity 0.139. So therefore, rearranging for t, we get t equals natural logarithm of 2 divided by 0.139. And when we plug this into the calculator and round to the one decimal place, we approximately get 5.0. So this is rounded to one decimal place. And so we see that it takes 5 hours, or otherwise we see that after 5 hours, after 5 hours, the number of bacteria doubles. And so this answers part C question.